we are going to discuss about a very interesting topic, that is Pangaea. After learning this lesson, you will be able to understand the origin, formation and structure of Pangaea, as well as you can able to analyze the breakup of Pangaea and the resulting geological and biological impacts, and you can also evaluate scientific evidence and compare Pangaea with earlier supercontinents. Let us have a introduction on this. So, Pangaea, also spelled as Pangaea, was a supercontinent that existed during the late Paleozoic and the early Mesozoic eras, approximately 335 to 175 million years ago. The name originates from the ancient Greek words like Pan, which means all, and Gaea, which means the earth, reflecting the idea that all land masses were once united into a single vast continent. The concept of Pangaea is central to the theory of plate tectonics and helps in explaining the geological, paleontological and climatological pattern observed across modern continents. Let us have a discussion on historical background as well as scientific discovery on Pangaea. The concept of Pangaea was first rigorously proposed by Alfred Wegener, a German meteorologist and geophysicist, in 1912, while earlier thinkers like Abram Ortelius speculated that continents had once fit together, and Wegener developed the theory of continental drift, suggesting that continents had once formed a supercontinent, that is Pangaea, which later fragmented and drifted apart. Wegener's hypothesis was based on matching geological formations, fossil records and the jigsaw-like fit of coastlines, that is notably South America as well as Africa. Though initially criticized, that especially due to his flawed idea of centrifugal force as the mechanism, Wegener's theory later gained credibility with advancements in seafloor mapping and Arthur Holmes' the theory of mantle convection in the 1940s and the 1950s. Eventually, these insights led to the broader plate tectonics theory, which confirmed the existence and the movement of Pangaea. Let us know about the formation of Pangaea. The formation of Pangaea was a long and complex geological process that unfolded over hundreds of millions of years, primarily during the late Paleozoic era. It involved the gradual movement and collision of smaller continental landmasses driven by the forces of plate tectonics. The process began around 480 million years ago in the Ordovician period, when the ancient continent, that is Laurentia, comprising much of present day North America, started merging with Baltica and Avalonia to form a larger landmass called Euramerica, also known as Laurasia. Over time, this landmass continued to drift towards the vast southern supercontinent known as Gondwana, which included the modern continents of Africa, South America, Antarctica, Australia and the Indian subcontinent. During the Devonian and the Carboniferous periods, that is approximately from 419 to 299 million years ago, a series of powerful tectonic collisions between Euramerica and Gondwana occurred. These collisions not only pushed up major mountain ranges such as the Appalachian Mountains in North America and the Ural Mountains in Eurasia, but also contributed to the closure of ancient ocean basins like the Rik and Lepettus oceans. By about 335 million years ago, during the late Carboniferous period, these tectonic forces had brought together almost all the Earth's land masses into a single enormous supercontinent known as Pangaea. This newly formed continent had a distinctive curved or C-shaped structure with a large identification where the Tethys Ocean would later form. Most of the land was situated in the southern hemisphere, while the northern regions were drier and experienced more tectonic activity. Surrounding Pangaea was a vast global ocean which is called as Panthalassa, which occupied nearly the entire rest of Earth's surface. The creation of Pangaea marked a significant phase in the Earth's geological history, altering global wind and ocean circulation patterns, impacting the climate and setting the stage for both biological diversification and extinction events. It also represented one phase in Earth's continuing supercontinental cycle, which is a natural pattern of continental assembly and breakup that has occurred multiple times over the planet's 4.5 billion years history. Let us have a discussion on structure and geography of Pangaea. Geographically, Pangaea had a distinctive C-shaped structure with the central and the southern parts dominating the Earth's surface. Most of its landmass was concentrated in the southern hemisphere, creating vast interior regions that were far from oceanic moisture sources. At the heart of Pangaea was a massive inland basin which is surrounded by elevated mountain chains and plateaus formed from past continental collisions. The Panthalassa Ocean, an immense body of water which is surrounded by Pangaea on all sides, covering most of Earth's surface. To the east lay the Paleotethys Ocean, which eventually evolved into the Tethys Sea and played a role in the opening of the modern Atlantic and Indian Oceans. Pangaea's geographic arrangements significantly influenced global climate patterns, ocean circulation and the distribution of plant and animal life. Its breakup would later give rise to the present day continents. So, let us have a discussion on the climate of Pangaea. Pangaea's climate was characterized by extremes due to its massive size and compact configuration. The central regions of the supercontinent were far from the moderating influence of oceans, leading to hot and arid desert-like conditions. In contrast, the coastal margins were more humid and temperate. Climate models suggest that Pangaea experienced strong monsoonal patterns with seasonal rainfall near the coast and prolonged dry periods inland. Geological records such as sand dunes, evaporites and red beds indicate widespread arid conditions. Additionally, the lack of polar ice caps and the more equatorial positions of some land masses contributed to higher global temperatures. The overall climate was less variable compared to today, with the more uniform global temperature gradient, largely due to the unified landmass and restricted oceanic circulation.